Hello everyone, welcome back. This next section is going to be about vectors. So if you're in physics or if you've taken physics, you'll see some stuff that should look somewhat familiar. If you haven't, then I am going to teach you as much as we are going to cover here with vectors. So first, let's start with what they look like. A vector is usually something that has an initial point, which I'm calling P, and then a terminal point, which I'm calling Q. In fact, they look exactly like rays do in geometry, except that in vectors, this notation doesn't mean that this goes on infinitely. It actually stops at Q. Okay, so in the context of vectors, we start at P and end at Q. Okay, vectors have two things that are very important. They have what we call a magnitude, which means the same thing as length, okay, and a direction. Some notations. I believe the book will sometimes use the notation like this, PQ. So this notation means that P is the initial point, Q is the terminal point, and we're talking about a vector because we have a little ray, which actually means vector in the context of vectors. Sometimes you'll see, for instance, if I wanted to call this A, the book, since they have the ability to do bold letters, they will use like a bold lowercase letter. So this vector here can be written as vector PQ or vector A. Okay? Now, some examples in the real world of vectors, velocities are vectors. So for example, when you watch the weather report and you hear that there's a 20-mile-an-hour wind from the northwest, that means that there's actually a wind that's coming from the northwest direction towards us at 20 miles an hour. Okay, without the direction that it's coming from the northwest, all we know is that there's a 20-mile-an-hour wind gust. We don't really know where it's coming from. Okay, but the direction here, it makes it a vector. Without this direction, then all we have is wind speed. Okay, so the two things together, the magnitude or length, in this case 20 miles per hour, and the direction make it a vector. Okay, so that's one place where you see them. Forces that we'll talk about a little bit, and I'm sure you've done in physics, is another place. Okay, now some things that we need to kind of make sure that we all understand and are aware of. Okay, if I have a vector, for instance, that looks like this, PQ, and I have another vector that looks like this, let's call it AB, then the argument here is that vector PQ is actually equal to vector AB. And the reason that they would be equal, you have to have two things. They have the same magnitude. So if you look at P to Q and A to B, it looks like they're about the same length. Okay? And also the same direction. So because these vectors are exactly the same, pointing in the exact same direction and have the same length, we say that these two vectors are equal. In fact, if I took A, the initial point of vector AB, and slid it so that it landed on point P, then what you would have is that these vectors, when you put them on top of each other, would be exactly the same size, and I mean, you wouldn't have any bit of they would overlap exactly. They're the same. That's exactly what it means. Okay. Also, what else can we say? Just another note that might come in handy later. Vectors are parallel if they are multiples of each other. So for example, if I have vector AB, let's take it and move it down here, and I drew a vector that was the same direction, let's say, and call it C to D, maybe CD, and again this is just an approximation here, CD looks like maybe it's about twice as large as AB, so we would say that it's maybe double AB, and this works because, you know, if you take AB, slide it on so that A starts at C, you can see that this vector, when you move it so that it's on top of the starting point of CD, it lines up perfectly, it's on the same path, but it's not quite as large as it. So we can say that CD is double the size of AB. And as long as one vector is a multiple of another, we say that they're parallel. Okay? So therefore, CD is parallel to AB. Okay, so that's just kind of some background, notation and stuff like that. Actually, there's one more thing that I could write as far as notation goes. This is just naming the vector, P to Q, and this is just referring to vector A. If you see the notation like this, what looks like absolute value around the name of the vector, this actually means length or magnitude of PQ. Okay, so it does not mean absolute value of a vector. That doesn't make any sense. But we use that same notation to denote that we're talking about the length of PQ. So if you see the bars around PQ, that means we're talking about the length of PQ. Okay? All right, so again, this is just going to be a geometric approach. So we're not going to do anything too fancy with these things today. But we will kind of talk about what we can do with these vectors geometrically and what it all means. Okay, so let's start with vector addition. Which, by the way, we could also do subtraction, but we're just going to go very basic today. Let's say that this is vector U, and that somewhere over here is vector V. And we wanted to do or look at U plus V. So what does U plus V look like? Okay. What I will always do is I'm going to first take the second vector. So take second vector and connect it to first vector. So for example, the second vector, the one that I'm adding to U, that's V. So I'm going to take V and I'm going to translate it so that the starting point of V is going to start where U ended. Okay, I think this is also sometimes referred to as adding vectors tip to tail. And then likewise, if I slide the initial point so that it starts where U ends, I'm going to do the same with the end point of V and just translate that upward. So that now what I've done is created essentially another copy of V. So I've taken V, translated it so that now it connects to U. And now U plus V is simply going to be the vector that you create from the very beginning, which is the first point of U, all the way to the end of V. Okay? So this orange vector is considered the vector of u plus v, which sometimes we call the resultant. The resultant of u and v is going to be this vector here. Okay? If I wanted you to find this, we'll do an example in a minute. So if I put absolute value around u plus v, that means to find the length of the resultant. So after you connect the vectors and connect from the very beginning to the very end, what you would do is find the length of this orange vector, and that's what you would write for this question if it asked you to find the magnitude of u plus v. Okay? So now here's what this all looks like. Let's say that we have a point at A located at 3, 1 and a point at B located at 9, 7. So we're given these 2 points, and we're going to do several things. Okay, one, we're going to find AB, the magnitude of AB. That'll be part 1. And now let's say for part B, if P is at 0, 0 and Q is at 2, 2, find the initial and terminal points of AB plus PQ. And then the last thing we'll do is go ahead and find the magnitude of AB plus PQ. Okay? So let's draw a picture first. One, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That should be enough. Okay? So let's just plot these points. A is at 1, 2, 3, 1. So here's A. B is at 9, 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. So then here's B, and P is 0, 0, and Q is at 2, 2. All right. So first problem says find AB. So I'm going to connect A to B. Looks like my initial point is A. My terminal point is B. For part A, so over here I'll do all the solutions. We want to find the length of AB. Well, if I want to find the length from A to B, we can just use the distance formula. Okay, so AB will simply be the square root of 9 minus 3 squared plus 7 minus 1 squared. So we get 36 plus 36, which if we reduce is going to be 6 root 2. Okay, so that's the solution for part A. Oh, sorry, I should not drop this notation. So the magnitude of AB is going to be 6 root 2. All right, part B says to find the initial and terminal points of AB plus PQ. So what I'm going to do here is actually add the second vector PQ to AB. So let's see. PQ is from here, from P to Q. And remember that the idea is that you're going to, you know what? Just to make this example more interesting, I just realized something. Let's change this point, 0, 0. Let's change this to 1, 0. Okay? So I'm going to start. So P is going to be over here now. Okay, so if I had some whiteout, which of course I don't, well, we're basically going to ignore this little part here. Sorry about that. This will make the example a little better. Okay. So if we want to add the vector from 1, 0 to 2, 2 with the vector that's from 3, 1 to 9, 7, then what we want to do is slide this little green vector all the way to the end of AB first. And the easiest way to do that is to just put another point here at B and then just pretend that we've already done that, and then just copy the rise over run of this vector. That's the easiest way to do it. So, for example, from P to Q, it looks like I have to go up 2 units, go up 2, and then over 1 unit to get to the point 2, 2. So from 1, 0 to 2, 2, I have to go up 2 over 1. So now if I copy that, I go up 2 units and then over 1. Then this vector from here to there is another copy of PQ. I've connected it to vector AB. And now using what we talked about before, AB plus PQ is just going to be the vector that it goes all the way from A to this new endpoint up here. So if I draw this vector, this orange vector right here, that would be vector AB plus PQ. Okay? So to list the initial points, well, the initial point is going to be the same for the orange vector, because orange vector is the 2 vectors added together. The initial point is still A, so that's just going to be 3, 1. And now the terminal point is going to be a little different. So if I look at the terminal point, I have to figure out where this point ended up. So easiest way to do that, I know I don't have graph paper, so it's a little trickier, but this was 9 and 7 originally. And then I went up 2 units and over 1. So that means that instead of being at 9 and 7, my y increased by 2, so that's going to be 9, and my x increased by 1, so that's 10. Okay? In other words, from this point, which is 9, 7, if I go up 2 units and over 1, now I'm at 10, 9. So that would be the terminal point, 10, 9. So if you connect A all the way to the new terminal point of AB plus BQ, which is 10, 9, you get this long orange vector. Okay, so 3, 1 is initial, 10, 9 is terminal. The last part, C, says to find AB plus PQ, the magnitude of that. Well, we know that this notation just means to find the length of AB plus PQ. So we want to find how long the vector, this orange vector, is. Well, we didn't do this for no reason. We know where it starts and we know where it ends. So we can just do the distance formula again. If I do x2 minus x1, that's 10 minus 3. We square it. Then we do 9 minus 1, which is going to become square root of 49 plus 64. 49 plus 64 is the square root of 113, and I don't think that this radical reduces. So this would be the answer to the third question, which is to find the magnitude of the two vectors added together. Okay. Now we'll finish with just a couple of quick examples, just some more applications of vectors. Okay, so let's do something like this. Let's say we have two forces. Let's say force 1, and we know that this vector is 20 newtons. This force is 20 newtons, and let's call this force 2. And let's say that this is 13 newtons. Okay? So, I mean, and you can kind of picture what's going to happen here. If I want to compute the resultant force and direction, that just means that we're going to add this vector together with this one. So if you imagine, you know, like a force pulling an object this way and then another one pulling an object this way, in the end it's essentially going to move kind of in between the two. And you can see where that's going to move. If you slide F2 over to the end of F1, just like we've been doing, connecting tip to tail, now we have, and I'm always using orange for resultant, this diagonal vector. This is F1 plus F2. Okay? So then, in case you didn't follow that, I slid F2 over here, so now this is just another copy of it. And if I add F1 with F2, this is the resultant right here, this orange vector. So if I want to find the length of that, I could just do Pythagorean theorem here. Since I know that 20 and 13 are going to be the legs of a right triangle, we could say, yes, sorry, I forgot to mention that. This is a 90-degree angle to start. We'd have that this is going to be the square root of 20 squared plus 13 squared. So 400 plus 169, 569, square root of 569. I don't know if that reduces or not. I'm going to go with no since I'm almost out of time. So then this would be the magnitude. Now the direction, so let me just kind of redraw what we have here. So here's F1, here's F2. This hypotenuse was F1 plus F2. If we can find this angle out right here on the bottom, this would tell us the direction of the resultant force. We can find this angle using tangent because the tangent of theta is going to be opposite over adjacent, and we know that opposite was 13 and adjacent was 20. So if I do tangent theta equals 13 over 20, then I can do the inverse tangent of 13 over 20, which is going to be, make sure you're in degree mode, but about 33 degrees. Okay, so then here's how I would report the answer. It would say that the vector is root 569 newtons with the direction, and there's two ways to do this. If we're starting here, you can kind of think of this as the positive x-axis since we're going to the right. We can say 33 degrees with respect to positive x-axis. Or if you're in physics, you can kind of think of this direction as being east, and this vector is pointing north of east. So you could also say 33 degrees north of east. That would be the other way of doing it. Okay. One last quick problem, kind of also related to physics. Let's say I have a velocity vector that's 90 centimeters per second, and this is a 30-degree angle, and actually that's all that we have, sorry. And the directions say to find vertical and horizontal components. Okay, well, all that means is to find the horizontal part and the vertical part, if you were to make a right triangle, that would fit this description. Okay, and if we're looking for the horizontal part, okay, then that's not too bad. We have 30 degrees, so sine 30 is going to equal, oh, if I'm doing sine, sorry, that means opposite. Sine 30 is V vertical over hypotenuse 90. So 90 sine 30 degrees is the vertical component. Sine of 30 we know is 1/2. So we can say that the vertical component is 45 centimeters per second. Again, you can kind of shortcut this if it's a nice angle like 30, because it's a 30, 60, 90 triangle, so you probably already know the other answer. To find the horizontal, if you don't, you can do cosine, because this is adjacent and we have the hypotenuse. So cosine 30 is adjacent, horizontal, over hypotenuse, which is 90. So 90 cosine 30 is the horizontal component. The cosine of 30 is root 3 over 2. So then 45 root 3 centimeters per second would be the horizontal component of that vector. Okay? Alright, sorry about the length, but for some of you guys this might be pretty new, so I just wanted to make sure I did a good job of this. Alright, see you guys tomorrow.